Can it really be true? Can it? Alright. So, okay. Guys, I gotta show you something. Where's my sequence? Let's see. Oh yeah, here we go. This is mine, baby. Anyways, so I kind of went down a rabbit hole where I was trying to read Quantum Computing Systemocratus, and it was like too high level for me. So I'm like 4 chapters into this book, and this book is freaking life changing. I wish they had a class like the MIT class that's taught by this author at U Chicago, because it's super interesting. I mean, like I feel like I really have a pretty good grasp of what NP is, and and stuff like that. Um, I mean, I'm only right here at like the limits of computability theory, but it's such a good bedrock and such a good foundation. But that's not what we're doing right now. Okay, what we're doing is just, man, it's been so long. It's been so long, guys. All right, so I'm starting off in the middle of this because like I was already doing this for a bit. I feel like this stuff is coming back to me. All right, so what we're talking about is this equation, and this is like the phase graph or whatever it's called. And you can see here that, let's say we start it, the population is like epsilon bigger than 0. It's going to go boom, and it's going to asymptotically approach n. And then from the other side, it's also going to go to n. And from negative, wait, is it? From here, it's just going to go way off to the side. So in that Strogat's book, you'd have the arrow going that way, the arrow going this way, and then the arrow going this way. The long-term behavior of the population is very different for other values of the population. If the initial population lies between 0 and n, then dp/dt, or f of p, is greater than 0. In this case, the rate of growth is positive, and consequently the population is increasing. As long as p of t lies between 0 and n, the population continues to increase. However, as the population approaches the carrying capacity, the derivative approaches 0, so it sort of levels off. Oh, there's the plot. If p of 0 is less than 0, yeah, so it just like exponentially decreases. They don't plot the p less than 0. Oh, there we go. This is the whole thing. Yeah, I think he called it flows on a line. Alright, predator prey. We're about to do the exercises, but no species lives in isolation, and the interactions among species give some of the most interesting models to study. We conclude this section by introducing a simple predator-prey system of differential equations where one species eats another. Most obvious difference between the model here and previous models is that we have two quantities that depend on time. Thus, our model has two dependent variables that are both functions of time. Since both predator and prey begin with P, we call the prey rabbits and the prey rabbits and the predators foxes. We denote the prey by R and the predators by F. Our assumptions for the model are: if no foxes are present, rabbits reproduce at a rate proportional to their population, and they are not affected by overcrowding. The foxes eat the rabbit, and they have like a mass action law, right? And the rate at which the rabbits are eaten is proportional to the rate at which the foxes and rabbits interact. Which is, is it called mass action? I'm pretty sure it is. Without rabbits to eat, the fox population declines at a rate proportional to itself. So they die exponentially and rabbits increase exponentially, and they interact by a mass law. The rate at which the foxes are born is proportional to the number of rabbits eaten. By the foxes, right? Okay, so there you get a like conservation law kind of thing because it's equal. Which by the second assumption is proportional to the rate at which the foxes and rabbits interact. Okay, so we got the parameters. The first and third assumptions above are similar to the assumptions in the unlimited growth model. Yep. The rate at which the rabbits are eaten is proportional to the rate at which the foxes and rabbits interact. So we need a term that models the rate of interaction of the two populations. We want a term that increases if either R or F increases, but it should vanish if either R equals 0 or F equals 0. A simple term that incorporates these assumptions is RF. We thus model the effects of rabbit-fox interactions on dRdt by a term of the form minus beta RF. The fourth assumption gives a similar term in the equation for dFdt. In this case, eating rabbits helps the foxes, so we add a term of delta RF. Oh wait, but it's not, the parameters are different, so it's not, right, if we made this like a parameterless model, and it would just be R dot is equal to R times 1 minus F, and F dot is equal to F, or R minus 1. Yeah. Okay. It's called a first order system because there's only first order derivatives, and it's coupled because they depend on each other. It's important to note the signs of the terms in the system. Actually, one thing I never did when I looked at biomodels, I never actually looked at the graph theory of how coupled the models in the database are. Should do that. It's an idea. I'm trying to generate ideas for my final project, and that would be cool. Look at the, graph of coupling in biomodels, just to see what the structure of all of the, because this is like the body of like hundreds of years of people's effort. All right. Did they say that they're all greater than 0? Or all positive? That's funny. Foxes eat grasshoppers? That's funny. Okay. A solution to this system is, unlike our previous models, a pair of functions that describe the populations of rabbits and foxes as functions of time. Since the system is coupled, we cannot simply determine one of these functions first and then the other. Rather, we must solve both differential equations simultaneously. It is impossible to determine explicit formulas. So I've always disliked this in differential equations books. It's like so enigmatic. It's like, why not? They never give you a reason of why not. They just say it can't be done. Our discussion of the three population models in this section illustrates three different approaches to study. Okay, so we're ready to do these exercises. These exercises are not so bad. So I don't know if I'm going to do all of them. I know that I have to do, let's see which one. 1, 5, 15. It's 1, 5, 15, and I think 21. But maybe we should just read through them just to get a sense of like, if there's, because I feel like in my linear algebra book, the stuff that's in the homeworks doesn't cover everything. Okay, these ones are easy though. I already did these ones. Do we need to do them? Alright, well if they're easy, let's just do them. Alright, so the first one is clearly y equals minus 3. The second one is t equal to plus or minus 1, I think, because t minus 1 squared is equal to, oh wait, no, it's t squared minus 1. I'm pretty sure this is equal to t plus 1 times t minus 1. And then for y is equal to plus or minus the square root of 2. Okay, so that's that. All right, number 3. Consider the population model okay, so the zeros are, a equilibrium p is equal to 0, or I guess I should say p of t is equal to 0. No. It's just going to be p equals 0. It's not, I don't know. It's not important, really. And p is equal to 230. So those are the zeros of that equation. Now, it's increasing. All right, so we have like 3 points to check. Well, we don't really need to check the negative case. So we'll check p of 1, or p of t. We'll check p equals 1. So we're going to get 0.4 times 0.9 or something like that. And that's definitely greater than 0. So increasing from open on 0 to n. So that's the open interval because obviously we already said it's at equilibrium in the other ones. So it's increasing there. Let's see. If p is greater than 230, so let's say it's like 300. Then that's greater than 1. That's negative. So it's decreasing. It's the same as the one in the book. It's decreasing. So this is going to be like 230 to infinity. And it's also exponentially decreasing less than that, I believe. And so it's also minus infinity to 0. So it's only ever increasing in the 0 to 230. Okay, number 4. I just want to spam these so that it's like to just bang out a section of questions, just do it, you know? Okay, 4 is more complicated. P dot equals 0.3 1 minus P over 200 times P over 50 minus 1 times P. Okay, so there's clearly 3 roots. So fixed points are P equals 0, P equals 200, and P equals 50. I kind of want to graph this. What is the best thing nowadays to graph things? Desmos sucks. I really don't like Desmos. Well, let's just try to make the graph ourselves then. So, let's see, if P is less than 0, then it's going to be a negative times a positive times a negative. So it's actually positive. I'm almost positive. Okay. So then for, let's say P equal to like 25. So for P equal to 25, we're going to get, 25 times 0.3 times a positive, and then this is going to be a negative. So it's actually decreasing. Oh, so I think what this model is maybe is that if the population is less, if the population needs to reach, it's like an infant mortality type of thing. If the population is less than 50, while the second term is positive, and so is the third term, this one is going to be negative. So it hasn't, you need a baseline population of 50 somehow, otherwise you're going to die out. So then let's do P in 50 to 200. And so let's just pick 100 or something. So in this case, we're going to have like a positive times a positive times a positive, which is obviously positive. So it now approaches, it now increases. We'll just say it's increasing. And then for P greater than 200, we'll just say like 300, it's going to decrease. All right, so it's this, okay, all right. That was a good problem. Yeah, so this P, unless you're above population 50, you're going to die. And then the weird case is if P is negative, then you go to 0, but that's not really relevant. Okay, number 5 is actually a homework problem. So this one is clearly y times, so y dot equals y times y squared minus y minus 12, which is also equal y times y minus 4, y minus 3. So the zeros are y is equal to 0, 4, and this is positive 3, this is negative 3. Okay. And then for the increasing, decreasing, we're just going to test minus 1. So it's going to be minus 1. So it's going to be a negative times a negative times a positive. So it's actually increasing, right? Let me just evaluate one for real. So it's going to be minus 1 times minus 5 times 2, which is equal to 10. Okay. Now we'll check. Oh, wait, you know what I didn't do right, though? I need to check minus 4. So minus 4 times minus 8 times minus 1 is equal to minus 32. So it's actually, yeah, so it's actually decreasing on minus infinity to minus 3. Then from minus 3 to 0, it's increasing. And it has to alternate, right? If you have a 0, it has to alternate, or no? I don't think that's true. I don't think it has to alternate. Because you could have something that touches it and then comes back up, like a parabola. A parabola whose whatever basin is at as a crosses the x-axis. So then I guess we do have to test all the points. Man, it's been so long since I did this stuff. All right, so now we got to test 0 to 4, so we'll just test 1. So 1 times minus 3 times 4 is equal to minus 12. So it's on 0 to 4, it's decreasing. And now we check 5 times 1 times 8 is equal to 40, and it is increasing from 4 to infinity. Increasing. I kind of want to use typist. I really want to use typist to write out my stuff this time. All right, I'm going to get another cup of coffee. All right, so 5 is easy. All right, let's see, 6. Model radioactive decay using the notation. Oh, I didn't see this. In exercise 6 to 10, we consider the phenomena of radioactive decay, which, from experimentation, we know behaves according to the law. The rate at which a quantity of radioactive isotope decays is proportional to the amount of the isotope present. The proportionality constant depends only on which radioactive isotope is used. It's pretty amazing. It's kind of weird that the universe does have such a consistent, predictable, exponential function in it. Never really thought about that. Monday math. Monday math. Okay. So this is obviously for A. The R dr dt. Jesus. dr of t dt is equal to minus lambda r. I guess you could say minus lambda r of t. If the amount of the isotope present state the corresponding initial value problem. So these are the kind of problems where I feel like teachers get real bent out of shape if you don't give it in the form that's given in the book. But I don't know where they specify how you're supposed to write it down. Okay, you just write it like this. So it's going to be comma r of 0 equals r0. Okay, so that's what you have to do. Okay. All right. 7. All right. The half-life of a radioactive isotope is the amount of time it takes for a quantity of radioactive material to decay to 1/2 of its original amount. So if we have R0 is equal to R0, so then we have the additional parameter that at R of 5230 is equal to R0 over 2. Okay, let me just try to do it myself. So how do they want me to do it is my question, though. I think they want me to integrate it. So dr over r is equal to minus lambda dt. So we integrate both sides and we get ln of r is equal to minus lambda t plus c. Then we x both sides and we get r is equal to e to the minus lambda t plus c, which is equal to e to the c e to the minus lambda t. Because a sum in the x means you can drag it out. So this is constant though, so then we can just say c e to the minus lambda t is equal to r of t. Okay. so when r is 0, or I mean when t is 0, then we get c e to the minus lambda 0, which is equal to e to the 0 times c, which is just c. So c must be equal to r little 0. So that's all good. So our explicit formula for r of t is r of t is equal to r0 times e to the minus lambda t. So we know that 1/2, so that so 1/2 r0 is going to be equal to r0 times e to the minus lambda times 5230. And what does that mean? That means that we can get rid of the r0s, so it's just 1/2. Then we can take the natural log of both sides, and we get ln 1/2 is equal to minus 5230 times lambda. So this is going to be minus 2 is equal to, I'm pretty sure that's right. Hold on. Oh, really? Yeah, I don't know why I thought it was that. Okay. Anyways, it should be ln 1/2 over minus 5230. That's lambda. Let's see if I got it right. Okay, so we did that. Then we did that. Yeah, then we did that. Then we did this. Oh. That's what it is. I didn't remember that rule. That's okay. I didn't remember that rule that ln of 1/2 is equal to minus ln of the reciprocal. Okay. So yeah, so we got it right. Good. That's what I was expecting. All right, I don't feel the need to do this one again. That's the same exact problem. But C, what is the units? Whoa, that's weird. I have no idea. Well, let's try to work it out. So the dimension of R of t is in mass. Is it 1 over time? I think it might be 1 over time. That's my guess. Because then the t and it cancel time out, and then the x term is just a fraction. Yeah, 1 over time unit. Okay, I'm glad that I got that right. Yeah. All right. Very good. Okay, to determine the half-life of an isotope, we start with 100 atoms. For D, okay, so the answer for D is yes, you'll get the same answer because no matter what, it's going to be 1/2 is equal to e to the minus lambda t. So it doesn't matter. It's not dependent on, it's only dependent on the ratio of the starting and ending part. Okay. Number 8. Carbon dating is a method of determining the time elapsed since the death of organic material. Carbon-14 makes up a constant proportion of the carbon that... Wait, hold on. Carbon-14 makes up a constant proportion. Okay, but once it dies, it starts to decay. By measuring the amount of C14 in the organic matter, varying the amount of C14 typically found time since this can be determined. Using the decay rate parameter you computed. Did we do C14? Oh yeah, we did. Alright, we'll do one of these. I'm fine with that. I don't think I need to do all of them. But so basically we're gonna get 0.88 is still in the material. Okay, so we're gonna get 0.88 is equal to E to the minus lambda t, where lambda is equal to ln of 1/2 over minus 5,230. Okay, so that, oh, but that is, right, this is, okay, so let's just say, lam is equal to ln 1/2 divided by minus 5,230. Oh, geez, I keep forgetting that. Okay, so we want to do, so the unknown is t, so 0.88, so we're going to take the log of this, so we're going to get, like, the log of 0.88 is equal to lam, where lam is this, is equal to lam, minus lam times t. So then we're going to get, log 0.88 divided by minus lam is equal to t. Okay, so there we go. So now we found t. So we should just be able to do this. Okay, so it's going to take 964 years, 0.5 years, to reach 0.88. And we can validate this, right? Because, well, no, we're going to get the same expression back out. I mean, we could just do this, just to... Yep. All right, cool. Why do they do this? Using the time constant as the amount of time an exponentially decaying quantity takes to decay by a factor of 1 over e. All right, so if we did 1 over e is equal to e to the minus lambda t, then we took the natural log. Does this work if I'm not signed in? This is minus 1. So then if we take the natural log, we get minus 1 is equal to minus lambda t. So then we get 1 over lambda is equal to t. Oh, yeah, that makes sense, because that's like the simplest part. Okay, that checks out. What's up? What is up, Ole? I got so much freaking homework this quarter, dude. It's so much freaking homework. But it's actually good, because I never took a differential equations class, so I'm trying to get... And I never took linear algebra, so... I took linear algebra, but I just did horribly. I never, like, truly took linear algebra, I feel like. I just sort of skirted by. Okay, so how is the time constant? And I don't know what to say. The time constant, tau, is the amount of okay, so I see that it's the what are the time constants in terms of the half-life? Express the time constant in terms of the half-life? Okay, we'll think about that one in a second. I basically got the expression, but I don't know how to put it into words. I mean, I see that when you take the natural log, you get 1 over lambda is equal to t, but what does it mean? Yes. Wait. I got confused here. Oh, yeah, because that's what tau is. Oh, yeah, okay. Right. This is tau. Right. Yeah. Okay. That checks out. So tau is the reciprocal of lambda. Okay. Yeah. That makes sense now. Express the time constant in terms of the half-life. Whoa, I don't know how to do that. Dude, what you been up to? I've just been grinding this homework, man. Just doing it. Linear algebra has like so much homework. Okay, wait, what? The half-life. Okay, the half-life is the expression where you have 1 over 2 is equal to e to the minus lambda t. So then you get this, right, so the half-life wait, so up above in 6, we knew the half-life. So we knew the ratio from the current time from the start, and then we use that to determine lambda. But once we have lambda, so the half-life is going to be t is equal to minus ln, or ln 1/2 over minus lambda. So this is half-life. I guess it simplifies to ln of 2 over lambda. So expressing tau so it's just going to be tau times ln 2, I think. All right, that's my guess. This is the answer. All right, and I don't think I want to do all the computation ones. I just want to do the ones that are more like thinking problems. Given an exponentially decaying with an initial value, show that its time constant is the time at which the tangent line to the graph show that its time constant is the time at which the tangent line Wait, what? R of... How is that possible? Okay, I definitely want to do D. Alright, let's make sure that we got the answer right for B. Oh, yeah? Dude, Bevy? That's cool. Have you made anything? Oh yeah, wait, is equal to t, but what we need to do is we need to change it around so that tau is equal to t over ln 2. Oh, but t, where t is the half-life, right. So let's make this like that, like that, like that. Because if it's just t, then I don't know what it is. That is definitely the best way to write that. Okay. I'm going to skip C. I'm just going to go to D. Given an exponentially decaying quantity. Okay, so we know that R of t, and let's just assume that R0 is equal to 1. It simplifies the math. Then this is going to be e to the minus kt. Or pt. I don't know. So if we want to plot that, let's just say p is 1. So then we literally just have R of t is equal to e to the minus t. So then we're going to say plot e to the minus t. And it's saying the time constant is when it crosses the t-axis. But that doesn't make any sense. Wait, the time constant is 1 over e is equal to e to the minus t. So then we do minus 1 is equal to minus t. Is it that? But I don't even understand this one. Dude, I've been playing so much tennis. Tennis is so fun. Oh, dude, you weren't here when I showed this, but hold on, let me. Oh yeah, yes. Check this out, man. So I've been reading this book on the theory of computation, and I came up with this sequence, and it's mine, and it was approved. How cool is that, man? Author Anand Jain. I have two other sequences that I have drafted, but I haven't. I need to like clean them up a little bit. Okay, let's see what did it say. Oh, when the tangent line, at the time at which the tangent line to the graph crosses the t. Okay, wait. So if with that, I'm not going to read any of the rest because now I get it. So if we have this plot like this, right. So so if t is 0, e to the 0 is equal to 1. So yeah, so that's true. And then the slope of this I want the step by step. Let's. Wait. How do I get that? No. Okay, the tangent line. Yeah, this is what I don't remember. Find the tangent line at 0. Oh, so we just need it. Yeah. So okay, but so you get minus e and minus t. So the derivative's right to find this tangent line slope at t equal to 0, we just say e to the minus e to the 0 is equal to minus 1. So the slope so I'm pretty sure that so f of x is equal to minus x plus 1. Because this is, let's say this is y of 0. Wait, no. Hold on. I jumped ahead. So this is the slope. Okay, I'm writing the equation of the tangent line. Y of 0, what is y? This is the non-derivative. This is e to the minus t. So y of 0 is equal to 1 plus the derivative, which is at the derivative at 0, which is minus 1, times t minus 0. Okay, yeah, I said x, but this should be t. Do 1 minus t. And we just got rid of the lambda. So now to find the 0, say t equals 1. Or if we had a param for lambda that's not 0, then it would be 1 minus lambda t is equal to 0. So then t equals 1 over lambda. Which is equal to the time constant. That's kind of weird. Okay, so wait, let me read the problem again, now that I get what is going on. What a weird thing. Huh, okay. It is often said that exponentially decaying quantity reaches its steady state. Okay, so let's see if we have, so we want to find how much is left, the ratio. So we're going to get like r of t over r0 at t equal to 5 tau. And tau is a number that we can always just like write down. Like it's an explicit number for any given parameter, right? So if we say lambda is so what is tau? Tau is 1 over e is equal to e to the minus t. So then we get minus 1 is equal to minus t equal to 1, or tau equal to 1. So if we just say it e to the minus 5, what is that? Okay. So like less than 1% is left. of course it's not actually true. That's obvious. That was a good problem. I like this one. So, yeah, so anyway, so x of minus 5 in the case of lambda equaling 1. Yeah, okay, so we got the same number. So yeah, so it's like the point where less than, or where about less than 1% is left. Okay. Should we do some of these written problems, or should we just move on? Hypertension, when administered, accumulates in the thyroid gland where it decays and kills that part of the gland. That's kind of a fun problem, but I think I'm good on that. Because this is just evaluating the exponential at certain time points. This answer is never right. Okay. Gotta watch the clock. I have some other stuff. Oh, shoot. Okay, so I only have like 30 minutes left. I'll be back later. But, okay, so for 11, we have r dot equals kr. So then we have r of t is equal to e to the kt. This is r0. So we're going to say r0 is r of 0 is equal to 4,000. And t0 is equal to 2,000. So what am I trying to say? I'm trying to say that e to the k0 is equal to 1. So then r0 is equal to 4,000. Okay. Then for e to the k, what is it, 6? Are we saying 6? Is equal to 130,000 over 4,000. So just figure what that out is. So this is 130,000 divided by 4,000. Okay, and this is going to take the log of this and divide by 6. Okay, so it's going to be k is equal to 0.580. That was pretty easy. I'm going to double check my answer, but I'm going to double check anyways. Nice. Oh, I didn't see that second part of the thing. What does the model predict for you? Okay, so let's just do that. So then let's do, so this is k. So now we're going to do x, k, 10k. 330. Wait. Oh. So the answer at t equal to 10 is 4,000 x of k 10. All right. Whatever that is. Ooh, that's interesting. All right, see you later, man. Let's see. I'm actually curious. So, if v dot is equal to kv squared, then we get. Well, so okay. The question is, what is the integral of 1 over v squared? So say there's no k. I like to get rid of the parameters and just do it how it is. So is equal. So we know dv dt is equal to v squared. So then we get dv over v squared is equal to dt. So we get is equal to t. Wait, hold on. V minus 1 over v is equal to t. So wait, no, that's not right. What I'm trying to say is it should be growing faster, right? Wait, I need to come back to this. This is weird. Okay, given that I don't have that much time, I do want to actually finish the real homework problems. Let's skip to 15. I would like to come back to it, but you kind of just have to finish it. Okay, so consider the following two differential equations that model students' rates of memorizing a poem. Ali's rate is proportional to the amount to be learned. So, okay, so let's say LA and LB are the fractions of the poem learned. Okay? So, the amount not learned, so amount not learned is 1 minus LA for Allie. Okay, so let's find the zeros. So wait, we have LA dot is equal to 2 times 1 minus LA. And LB dot is equal to 3 times 1 minus LB squared. Okay, so first, all we have to do is just evaluate. So at t equals 0, we can assume LA equals LB equals 0. Therefore, 2 times 1 is equal to LA of 0 dot. And LB of 0 dot is equal to 3 times 1 squared. Therefore, what is it? Beth is learning faster at t0. So that is A. B is okay, so now we compute LA equal to 2 times 0.5, and LB dot is equal to 3 times 1 minus 0.5 squared is equal to 3/4. And this is equal to 1. This is going to be 0.5 squared equal to 1/4. So Allie C. So for C, it's 1/3, so it's going to be LA so 2 times 2/3 versus 3 times, this is going to be 1 2/3 squared is equal to 49 times 3 equal to 4/3, and this is going to be 4/3. They are equal when okay, great. So we did 15. Now we're just going to really quickly do 21. Let me get my hat. Alright, let's just do it. So, okay, so in the following predator-prey system, identify which dependent variable x or y is the prey population and which is the predator population. Is the growth of the prey limited by any factors other than the number of predators? Do the predators have food sources other than prey? Okay, so here, x, let's say y is 0, then x is the x dot is equal to minus alpha x. So this is going to decay exponentially. Okay, so that means that this is likely the predator. So in A, x is likely the predator because it decays x when no y present in system. For F, okay, so that answers the first part. Now is the prey, so y is prey. Is the growth of the prey limited by any factors? No limit on prey growth other than pred. We can see that if x equal to 0, then prey grow exponentially. Similarly, for pred, no other food. Okay, for B, Y is pred because their growth, it has a term of xy, meaning the interaction between pred causes pred growth. Prey has a, so I don't know why it's squared, but has a carrying capacity relative to x squared. And the only other part that we need to answer is the growth of the prey limited by any factors. It has a, which is from environment or something. And pred must have food elsewhere, as if no prey, pred still grows x. Okay, so that's all the problems in the homework. So I'm basically going to put a link to this in my write-up of the actual solutions. But we did all the problems, and we did them in earnest. I would like to go through some of these other ones at some point. I was really curious about this this one. But we did them all. I think 1, 5, 15, 21. Is there more? Let me check on my phone. Canvas, canvas, canvas. Yeah, 1, 5, 15, 21. Okay, great. Cool. And it's due tomorrow at midnight. All right, nice. That concludes this stream.